with soft limits of scattering. And also this so-called memory effects, which I'm not going to talk about at all, I'm just mentioning it so that you know. And the connection here is that actually, if you write down a Ward identity for some asymptotic symmetries, then these become a statement about the amplitude for some scattering process within the limit of some gauge boson going to zero energy. So let me remind you about what these two ideas are. So Weinberg, so soft graviton and soft photon theorem from 1965. That's what we're going to be talking about on the right side here. And so this is a statement that if you have some scattering amplitude with some photon with momentum p, which we're going to take to 0, and some other hard particles, but this amplitude can be rewritten in the limit of this photon's momentum going to 0 as some multiplicative factor called the soft factor. I'm supposed to start writing smaller over here. Anyway, maybe that can be done in post-production. So it's this multiplicative factor times the amplitude with no photon. So this thing is called the soft factor. P gamma is the momentum of the soft photon. Epsilon is the polarization vector of the photon. And then we're summing over the outgoing hard particles, and then summing over the ingoing hard particles. Qk is the electric charge of the kth particle. And there's a similar result for the graviton. So this is the photon, obviously. For the graviton, no, for some reason I wrote Q here, but I'll just do it. So it's very similar. I have some soft graviton, and then hard particles. So I have kappa over 2. Kappa is a square root of d Newton. And then here I have sort of the obvious thing. Like this. And then minus some of the ingoing guys, and then times the amplitude without the soft graviton. These are interesting. Well, you know, where you might have seen them is in any treatment of infrared divergences. This is sort of the first step in showing that infrared divergences cancel out. So you can use this approximation to be able to actually resum all the infrared divergences. There are also useful constraints on in amplitudology, so you can use these to constrain the form of general amplitudes, and they're used in that way. And there are various generalizations of this, but let's just focus on this simple case. And the idea is that this soft graviton theorem is going to be related in some way to BMS. So let me remind you what BMS is. Since this is sort of the original motivation, then I'll change gears slightly. So if you look at asymptotically flat space near scribe plus, and you choose some retarded coordinates, then you want to look at diffeomorphisms that preserve asymptotic flatness near scribe plus. It's very similar to like what Brown and Hill did in EDS3, although that was much later. It simplifies life to work in so-called Bondi gauge. Where G are R and G are A, where this is the spherical coordinate, vanishes, and gives condition on the metric on the sphere. And this is a general gauge. You can locally always do this. But in this gauge, I'll have some follow-up conditions based on, or that I determine from the behavior of gravitational waves near scribe. So in particular, the UU component follow up like 1 over R, UR, correction should fall off like 1 over R squared, UA should be ordered R to the 0, and AB should be R squared times the metric on the round 2-sphere plus order R corrections. So then you look for diffeomorphisms that preserve these boundary conditions, and for simplicity I'll also demand that it stays in the Bondi gauge. And you find BMS vector fields, which look something like this. All right, like this. So I just mean that it's a function on the sphere. So that's the U component of the vector, and then I have explain notation here in a second. Then there's some other stuff here, and that's the R component. This is actually fixed by the Bondi gauge. So f is an arbitrary function on the sphere at infinity. When f is an L equals 0 mode, meaning a constant, then it's just time translation. When it's an L equals 1 mode, then it's exactly translation. It's a killing vector of the vacuum. But I have these other generalizations of the ordinary translations. So those are called super translations. In this vector field y, I require it to be a conformal filling vector on S2 in the sphere at infinity. And if it's one of the globally well-defined conformal killing vectors on the sphere, then I get the boosts and rotations. But if I allow myself the freedom, which has recently been considered, to consider general conformal killing vectors on the two-sphere, I have an infinite number of conformal killing vectors in 2 dimensions. Then I'll call those the super rotations.
They have singularities, though?
Yeah. So the idea is that
What was this distinction between super translations and super rotations?
so I have I have 2 sort of parameters in my vector field. One is a function f on the 2-sphere, and that's independent from this vector y. So when f is a higher than L equals 1 mode on the 2-sphere, I'll call that a super translation. And when this vector field y is a general conformal killing vector in the 2-sphere that has singular points, then I'll call that a super rotation. So the idea will be that the super translations the super translation ward identity, which I'll try to convince you exists, will be essentially Weinberg's soft graviton theorem. To be more precise, it'll actually be omega squared times the left-hand side and the right-hand side, where omega is the energy of the soft graviton.
And is there a super rotation ward identity?
There is. It's a little more mysterious, but it appears to be related to. There's another term in an expansion in softness that's subleading to this leading piece. And that piece you can relate to the super rotations.
Subleading means in an expansion in powers of Q, essentially?
Yeah.
And the soft photon theorems come from a similar thing, but for the gauge?
Yeah. And in fact, I was about to say, for simplicity, I'm going to focus my discussion just on the soft photon story, because gravity is more tedious, and I don't think I'll have time to do it all on the chalkboard. But I wanted to present this first because this was sort of the original motivation, even though Ingles and E-T is much simpler. Yeah, so instead we'll do talk about food. So that's where we're headed. But to get there, I'd like to take an approach. The approach that we're advocating is motivated by a very old question that's been treated many times in the literature, although I'd like to argue that a lot of people haven't gotten it right, which is what are the Mercer charges / theorems for local symmetry? So what I'm going to try and argue is that once we understand this, it's straightforward to apply that in a path integral formalism and write down ward identities, which will right basis, be exactly the soft photon, and in the case of gravity, the soft graviton. Where our approach differs from what Strominger and friends have done is that they have primarily used a canonical approach, and in general they have not been very precise about what they're doing in terms of gauge fixing. In every paper they actually switch gauges halfway through the calculation without telling you. Although I think the answer is actually correct. But, and so it was out of frustration with just with the canonical formulation for quantizing gauge fields near null infinity is kind of hairy and confusing, that we developed this approach, which we think is much clearer. So just let me, so this, as I said, this has been treated many times, this question, but the references that we found particularly useful are these papers, so let me just put them so it's clear that I'm not getting total credit here. And there's also a nice entire book by Kosten and Schwarzbach on the history of Noether's thing, which is just a funny thing. Okay, so we'll go back to undergrad physics for a second. Noether's, I'll put in parentheses, first theorem.